Yeah. All right. Good evening, everyone. Welcome back. Hope our tests went well. I have not had an opportunity to look over those yet for partial credit. I was actually trying to do that this afternoon, and my math lab would not let me in for the past hour or two. Sometimes it happens. No big deal. First thing I want to point out, I did have a typo on the board last time. I said 4.2 was going to be due on the today. There is no 4.2. Obviously, we were working on 4.1 and 4.3. So I'm just going to say I'm going to give you a week from today. 4.3 is due on the 4th. We're also going to get through most of 4.4, pretty much everything except for one example at the very end, as long as nothing goes wrong like last week. So I'll just hold off on assigning that as well. So 4.3 should just be what you have until 4.4. And yeah, besides that, let's just pick up where we left off, working on those integrals, on those definite integrals where we had not just to do the regular formulas, but we had numbers on the integral symbol and we had to evaluate them at the upper and lower bounds to find the area under the curve. And then we'll extend that concept as always, and then move on to something else more interesting. But all right, here we go.
Example 2. Wrong color. And we are going to do the same thing. Find the area under a curve. Given function and bounds. A, we're going to do the integral from 1 to 5 of the function dx over x. So this you might think is the power rule. You might say bring the x to the top and then you got an x to the -1. Add 1 to the exponent, divide by the same. But -1 plus 1 is 0. And that's that one and only one case we said the power rule fails on. You can't use the power rule here. You have to go back to the natural log exponential rule. It's frozen on me. There we go. Da, 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 da. This thing is being really bad right now. There we go, finally. Probably because I've tried to open too many files. It's probably going to crash on me, if I had to guess, in the next 30 minutes, but that's okay. So we said when you have to integrate 1 over x dx, you get the natural log of the absolute value of x. And that was because the derivative of the natural log is 1 over x. But we said we had to remember this absolute value. This is something a ton of calculus students forget. If I don't tell you x is positive, you need this absolute value. If I do, then you don't write it. Now, I wrote it this way, integral of 1 over x dx, but you'll notice on this example we have here, it says the integral of dx over x. It's the same thing. If you need to rearrange this, you can. Some students do, some students do not, but these are the same thing. So the integral of 1 over x is the natural log of the absolute value of x. But we're not doing a plus c, we've got evaluations, so we draw that extra line. L, absolute value, line for evaluations, that's a lot of bars, isn't it? Make sure you understand which is which. So natural log of absolute value of x evaluated between 1 and 5. Now, here's what's cool. I don't really need the absolute value for this example because 1 and 5 are positive. So I could drop it because the answer will be analytic either way. But it's just a good habit to have. So this will be the natural log of the absolute value of 5 minus, that's the upper limit, minus the lower limit, the natural log of the absolute value of 1. The natural log of 5, I have no idea what it is. You should have no idea what it is. I have a ballpark of what it is. It's between, this number and that number. But I don't know what it is to a decimal point. Minus, but I do know what the natural log of 1 is, and you are supposed to remember what the natural log of 1 is. So this is one of the things that was in one of those introductory review chapters that you have homework and notes on that you can go back and look at any time. But the natural log of 1 is 0. As a reminder, the natural log of 1 is 0. The natural log of e is 1. You will see those over and over and over and over and over. Now, well, what happened to the absolute value of 5? Well, the absolute value of 5 is 5, so I drop the absolute value. And then the natural log of 1 is 0. We don't need to write minus 0, so we just write the natural log of 5. If you're curious as to what that number is in size, you can pull out a calculator and get an estimate. Natural log button, 5, close it. It's 1.61 or 1.6 depending on how you like to round. But that's a rounded answer. Your homeworks, your teacher generally wants exact answers. So yeah, that's about 1.6, but I don't want to see 1.6 unless it asks you to round. If it's an application, you're probably going to round it. But this was not an application, so don't you dare. B. The integral from 0 to 10 of e to the x dx. I'm also going to remind you that the natural log of 0 is undefined. You can only take the natural log of positive numbers. You can't take the natural log of a negative. You can't take the natural log of 0. Natural log is only defined for positive values, hence the absolute value needed. Because I could say to evaluate the area under the curve of 1 over x dx from any number to any number, I just can't make the upper or lower bound 0. So integrating e to the x, we go back to our formulas that you're supposed to memorize. The integral of just an e to the x is e to the x. If there was a constant coefficient up there with the x, then you'd have to divide by that as well. So we're just using the simpler one. But you can still see this one all day, every day. So the integral of e to the x is e to the x. We're evaluating this from 0 to 10. So e to the 10, that's plugging in the upper limit, then minus. E to the 0, that's plugging in the lower limit. Don't you dare ever leave exponents of 1 or 0. Evaluate them. E to the 10, no idea. It's e to the 10th. Minus. Anything to the 0 power is 1. Anything to the 0 power is 1. That's the answer. That's all you can do with it. If you want approximation, if this was an application, once again, you can pull out your calculator. E raised to the 10, close my parentheses, minus 1. And it's about 22,025 roughly. That's a big number. So the area under 1 over x from 1 to 5 was a tiny number, like 1.5 roughly, 1.6 I think, yeah, 1.6. But the area under the curve from e to the x from 0 to 10, it's twice as wide as last time roughly. But this e to the x function is so much higher than 1 over x as you move on, that that area is a much larger number. Look at the graphs of these things. Here's 1 divided by x versus e to the x. But you're supposed to remember what these look like from pre-calculus. There's 1 over x, and it's got that vertical asymptote. Here's e to the x. So if you're finding the area from 1 to 5, I mean, you're in here. You're in this tiny little region. That's not going to be a very large area. That's why it's only like 1.5. But if you're doing e to the x from 0 to 10, I mean, this thing is off the chart by the time you hit 3. Trace, 2. Wrong function. Let's hit up. There we go. 2. The height's 7.3. If I do 3, I'm already out of this window. I'm at 20. If I go to 10, the height of e to the x at 10 is 22,000 and some change. So we're way up at 22,000 by the time we get to 10, which is why this area is so massive. Because exponential curves, not fervs, exponential curves grow very rapidly. 1 over x is actually a descending curve. It does not grow. It shrinks. All right. Let's do another. All of the ones we've seen so far were just single terms. Let's get into one that's got an addition or a subtraction. We need to mix this up finally. So the integral, and let's get weird with it. From e to e squared of the function x plus 1 over x dx. Now, if that was 1 over x squared, you'd bring it to the top and make it x to the negative 2. Hold on, I got to cough again. If this was 1 over x squared, you'd bring it x to the top and make it x to the negative 2. If it was 1 over x cubed, bring it to the top, x to the negative 3. And those would be power rules. 1 over x, nope, it fails the power rule. That was the natural log rule. I'm not going to flip back to that page again. This x counts as x to the first. So when you add 1 and divide by the same exponent, that's x squared over 2. Plus the integral of 1 over x dx is the natural log of the absolute value of x. But then we're evaluating this thing between the upper and lower limits, between e and e squared. Which is like between 2 and some change and 8 and some change, roughly. All right, let's plug in these upper and lower limits. And I forgot to switch my color. That's frustrating. When I plug in the e squared, when I plug it into this x, that's e squared squared over 2. That's plugging the e squared into here. Now let's plug it in here. So plus the natural log of the absolute value of e squared. Again, in this red ink, all I have so far is just plugging in the e squared into the previous function. Then we're going to need to subtract. So minus, and because the next part has got multiple terms, we're going to need parentheses. Now we're plugging in the e into the original integrated function. So e squared over 2. It's not e squared squared anymore, so we're just plugging an e in here. And then plus the natural log of the absolute value of e. Looks like Linlell, the natural log of the absolute value of e. Extend your absolute value bars however much you have to make sure you can tell those are absolute values and not more L's or 1s. We got some simplification we can do. E squared squared, multiply the exponents. Yeah, 2 plus 2 is 4, but you're supposed to multiply them. 2 times 2 is 4. So e to the 4th. So if that had been a 2 and a 3, we'd have e to the 6th. And then over 2. Plus, well, e is a positive number. Squaring a positive number is a positive number. So I don't really need that absolute value anymore. So that's just the natural log of e squared. You might want to do this, though, so that you don't think that the 2 is squaring the natural log, that it's squaring the e instead. I can distribute the negatives, so that's going to be minus e squared over 2 minus the natural log of e. Once again, e is a positive number. It's 2.71828, blah, blah, blah. So the absolute value of a positive is a positive. All right, well, there's some stuff we can do here. The e to the 4th over 2 minus the e squared over 2. You can't do anything there. You're stuck with those. That's e to the 4th over 2 minus e squared over 2. That's the first and the third terms. The natural log of e squared, this was another formula that you were supposed to have memorized back in pre-calculus. It says that if you have the natural log, and I'm just going to write this in natural logs instead of the generalized formula. The natural log of e raised to some number, some letter, let's write it as x. So the natural log of e to any exponent, this is just the exponent. That's, again, a formula that you're supposed to have memorized for pre-calculus and that is in the reminder sections from the beginning of this course. So the natural log of e squared is just 2. The idea here is the bases match. So this is like an inverse function of a function. Everything cancels except the argument being the 2. So that's a plus 2. Again, that 2 was from this because we had a natural log of an e with an exponent. So all of this jazz just cancels out, and the answer is the exponent. Minus the natural log of e, we said right here is 1. And there is one last thing we can do. 2 minus 1 is 1. So e to the 4th over 2 minus e to the 2nd over 2 plus 1. That is the exact answer. It's not a pretty answer, but exact answers don't have to be pretty. If you wanted to know approximately what it was, or if it was an application and you needed to know what exactly or what approximately it was, you just do e to the 4th, close it, divided by 2, minus e to the 2nd, divided by 2, plus 1. And it's about 24.5. Now I'm going to show you something really cool that is not going to be that helpful to you for analytic answers most of the time, but it's a good way to check your answers if you're not sure. Go to the graph, type in your function, x plus 1 over x. Hit the graph button. So this is what it looks like. It's kind of weird. It kind of looks like an x function with a 1 over x kind of attitude with that asymptote, but instead of just flattening out this way, it then starts growing. And that's because this is basically not a composition of these two, but a transposition of these two functions. It's going to have features of both. So it's got features of a line, and it's got features of the 1 over x. All right, so check this out. Hit second, and then trace, which brings you to calculate. Some calculations for graphing. Look at what number 7 says. That's the integration symbol f of x dx. Also look at what number 6 is. So that could tell you the slope at a point. So if we do number 7, it asks you to type the lower and upper limits. So that's where we're going to type the e and the e squared. That's kind of a pain, but you still can do it. Here's my e. There's my lower limit of e. My upper limit, I got to type second e squared, close parentheses, hit enter. It actually shades it, showing you what area it's representing. And look at that decimal value, 24.604547, 24.60454. It's just got a little bit less decimal accuracy in the graph because it's got other computations it's handling. These things are ancient, so it can only do so much at once. It only wants to display so much at once. But again, in terms of actual calculus, oh yeah, okay, I typed that in and I got my answer. It was 24, blah, blah, blah. You type that in my math lab, it's wrong. You do that on a test, it's wrong. You have to have the analytics here.
Just have to skip something really quick.
You have multiple terms. You really have to be careful when you're doing the lower limit evaluation because you've got to do the minus, you need the parentheses, and you have to distribute it. This is the number one simple mistake that students make is they forget to distribute the negative or forget the parentheses, which ultimately makes them forget to distribute the negative. They didn't think to have it there. Let's do another one. Integration from 1 to 2 of x to the negative 1 minus 4x squared dx. Okay, so this x to the negative 1, some of you may already know this is the natural log when you integrate it. but that's not exactly how I wrote the formula out. So I know that some of you will want to rearrange this first and go integral from 1 to 2 of 1 over x and then minus the 4x squared dx. It's up to you if you need to do this rewrite or not. If you can go straight from this to a natural log when you integrate, you can skip the rewrite if you want. However, I would say it's probably a good idea to do the rewrite. That way a month later when you're looking at your notes, you don't get confused. But again, we'll be able to power rule the 4x squared. We can't power rule x to the negative 1 because adding 1 to negative 1 gives you 0. Then we divide by it and we get undefined. All right, so integral of 1 over x is the natural log of the absolute value of x. I never said anywhere that x had to be positive. Again, in your homework, they might do that. If they do, drop the absolute value. I also have a typo here. It was from 1 to 2. I wrote 1 here. That's 2. Please make sure you correct that. So the integral of the 1 over x is the natural log. Then minus, leave the 4. Integrating x squared, add 1 to its exponent and you get 3. Then divide by the same value. And now we're doing this evaluation, the upper and lower limits between 1 and 2. So now we just plug those in. So we get the natural log of the absolute value of 2 minus the 4/3 don't cancel. So 4 times 2 cubed over 3. So that was plugging in the upper limit. That was plugging in the 2. That's what we get here. I'll show the subtraction of limits in a different color. So here's the minus. So the red before and after is the upper and lower limit. Now let's plug in the 1. So the natural log of the absolute value of 1 minus 4 times 1 cubed over 3. The absolute value of 2 is 2, so we don't need the absolute value. That's just the natural log of 2. 2 cubed is 8. 8 times 4 is 32. That's minus 32 over 3. Then this is the minus sign. And can anyone point out my mistake? I did this intentionally. This is where someone would say you didn't put a parentheses around it. Remember, when you're subtracting your lower limit, you've got to make sure you put your parentheses around it. So now I'm going to distribute that negative. So minus, and then the natural log of 1, we said earlier the natural log of 1 is 0. You have to memorize that. Oops, wrong color. But for the next term, it was originally a minus, but now there's another minus. 2 minuses cancel. So it's a plus. 1 cubed is 1. 4 times 1 is 4. So that's plus 4/3. Natural log of 2, no idea what it is. Leave it alone. Negative 32 over 3 plus 4 over 3, they have an LCD. Negative 32 plus 4 is negative 28. That's a minus 28 over 3. You don't need to write the minus 0. So that's it. You can't do anything else with that. That is the exact analytic answer. If you're curious what it is, you can put it in a calculator. I love doing this. So you get an idea what things look like. Natural log of 2, close it, minus 28 divided by 3. Negative 8.64, blah, blah, blah. So this area is negative, which means maybe there's a positive and a negative portion, but the negative area is bigger than the positive area. Or maybe just the whole area is negative. Let's see what the graph would look like. So we're doing x to the negative 1, which we said is just 1 divided by x. I could write it either way, it wouldn't matter. Then minus the 4x squared. Ooh, that looks a little weird. It kind of takes this sudden change at 0. And we're only going between 1 and 2, so let's make my window a little narrower. Let's make the x minimum negative 1, and let's make the x maximum 3. So again, because of that 1 over x, you have that asymptotic feature where it goes down to negative infinity, jumps over 0, and then goes up to positive infinity. And that's caused by the fact that we can't divide by 0. But then on the right side, it looks kind of weird. Integrating from 1 to 2, this height's not quite all the way there. Let me make my y minimum maybe negative 20. There we go. So we're just doing from 1 to 2. So we're slicing it from here to here. And it's not going to be this area down here. It's going to be this area here because we're going between the x-axis. So let's go second, calculate. Option number 7, that's our integral. Lower limit of 1, hit enter. Upper limit of 2, hit enter. It draws the shaded region that we're computing, and look at that, negative 8.640186, negative 8.640186, blah, 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 blah. So again, the answer is not negative 8.6, blah, 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 blah. It's natural log of 2 minus 28 over 3. That decimal version is not going to give you any points if it's not an application problem. And if it's a test, I'm going to go back and look for your work for all application problems of this test. Trust me, I will. And if all I see is just a decimal answer, I don't see the actual calculus, I reserve the right to take away all of your credit. I do not care that you can pull out a calculator and hit some buttons. I care that you understand all of the analytics behind it. That's what's important. All right, how much space we got? Good. E. Let's do the integral from -1 to +1. Ooh, symmetry, so maybe we could just use an argument of something. Maybe, maybe not, let's find out. 5e to the negative x. So maybe you graph this thing and say, is there any kind of symmetry? So y equals, clear, 5e to the negative x. So 5, second e, negative symbol, x. Now let's go back to a standard zoom. And if you know anything about exponential graphs, you know they're not symmetric. It's way higher on the left, it's way low on the right because of the negative. These would be flip-flopped if it was a positive. So we cannot use any kind of symmetry argument to say, oh, just do from 0 to 1 and then double it, or go from 0 to 1 and say they cancel. There's no canceling, there's no doubling. We're stuck with the calculus. And we could even go ahead and get the decimal approximation if we wanted to. We're going from -1 to 1, so we can go to the calculator part. Option 7, type -1, hit enter. Type +1, hit enter. There's the area we're going to find, and it's about 11.75. But again, I don't care about that. If it's an application, that's awesome that you have that answer, but you still have to be able to do the calculus. There's no funny rules here, really. There's no pluses or minuses, so there's no separating terms. This is just integrating e to the negative x, but the negative does throw this off. So going back to those rules, we said the integral of e to the x is just e to the x. But if there's an extra coefficient up there, you have to divide by that same coefficient. It kind of feels like the power rule in that regard, except you don't add 1 or subtract 1, you just make the exponent the bottom number. Okay. So that a is a -1 for this case. So note a equals -1 for the formula. The 5 out front, just leave it. The e to the negative x stays e to the negative x when we integrate that, but then we also have to divide by the -1. Again, because this a was a -1, the formula states that's still in the exponent, but you also divide by that value. If you don't trust this, take the derivative of what you get, and you should go back to the original 5e to the negative x. But we're evaluating this from -1 to 1. And we can clean this up. Dividing by -1 is the same as multiplying by -1. So it's -5 e to the negative x, evaluated between -1 and +1. That's -5 times e to the negative, so that's all part of the function. The -5, the e, and the negative, that's part of the function. Now I'm plugging in the upper limit, which is the +1. So I'll show the plugging in this time in blue because of the double negative situation about to happen. All right, then the minus for the subtraction of the upper limit and the lower limit. I don't need a parentheses around this because it's a monomial. All right, so now we're taking this thing right here and we're plugging a -1 in. So actually, we do need a parentheses because of the -5 up front. So -5, e. Oops, those are all supposed to be in red. -5, e to the negative, that's the function. But then we're plugging in a -1, which looks like that. Lots of double negatives. That's what I love about this problem. So what we get is, and let's go down here. The -5 e to the -1, we don't really want to have answers in that format. But let's leave it for now. Let's just see what happens with the other part. So -5 e to the -1. I'm not changing anything from the first part yet. These two negatives will cancel and make a plus. 5e. These two negatives will cancel and make a plus. 5e to the 1. These do not cancel and make 0. E to the -1 plus e to the 1 is not 0. These are very different from each other. E to the -1 means there's an e in the bottom. So it's -5 over e to the +1 plus 5e to the +1. And with exponents of +1, we really don't like to write them. Again, before in this format, that's not really an acceptable analytic answer because we don't like to see numbers raised to negative exponents. It's okay having a variable in there with the negative exponent. That's an okay format. But once you start plugging numbers in, you're supposed to clean them up like this. So that's something to be very, very careful of here. All right, example 3, and let's get to a word problem finally. Let's get into some of this stuff where we actually have some analysis to make. And actually before that, I want to make sure I point out something before I do the example. I'm sorry. When you're given a value as a rate, and ask for a total amount over a period of time or units of production, typically you are integrating. In other words, a total accumulation at a rate f from a to b, so f being the function, your given rate, and let me write that as f of x. I don't know why I just wrote that as f. So given so if you want to find a total accumulation at a rate of f of x from a to b, so you're given a function that's a rate, not an output. It's not telling you how many are made. It's telling you the rate of production. Then the total accumulation is equal to the integral from a to b of f of x dx. Example 3. Finding total amount tested. All right. Technician can test people for a virus at the rate of and I don't have to write this as f. I could just give you the rate. F of t equals -3t squared plus 18t plus 15 people per hour for a range of 0 to 6. T is the number of hours after 9 a.m. How many people between 10 a.m. and 1 p.m.? So what we have here is a function that tells you how quickly these people can get some testing done. And if you've ever had a job in your life or done anything in your life, you know that you are not having the same productivity rate at 9 a.m. as at 5 p.m. if you work from 9 to 5. You're probably slowing down right before lunch. You're probably at your slowest maybe an hour after lunch, something like that. Or maybe you really get your energy back and you have peak productivity in the middle of the day. Some people have peak productivity in the beginning and just go down in productivity all day. Some people come in and are barely doing anything and just get more and more productive as the day goes on. Every person has got a different productivity rate. So this technician, his rate has been found to be negative 3t squared plus 18t plus 15. But we're saying that it's only valid from hours of 0 to 6, being the number of hours after 9 a.m. So this is only for his first 6 hours of work, or maybe this is just his full workday. Maybe he only or she only works 6 hours of the day. And that's the thing about models. We've said that very often we need to have bounds on the independent variable, because this function, if I go to say 300 hours, this function would be absolute trash in talking about productivity, because you can't have negative productivity, and plugging in 300 hours would definitely be negative in this function. So this function is only good from 0 to 6. Maybe you're curious what the function looks like. Let's graph it. So again, just curiosity for now. Negative 3x squared plus 18x. I'm not using t's in the calculator because it doesn't work that way. Plus 15. Do a standard zoom. And that's not the best picture. We don't really need to worry about negative productivity, so we don't need any negative y values. We clearly need to see some higher y values. And going from 0 to 10 is fine because we really only need to see 0 to 6. In fact, let's just go from 0 to 6. So let's maybe triple the y maximum. Let's make the y minimum 0. And let's make the x minimum 0 and the x maximum 6. Let's see how that looks. Yeah, still not high enough, so let's play with the window a little more. Maybe the y max could be 50. There we go. So this is our graph. This is our productivity rate, which is all positive. So it looks like we're doing okay at 9 a.m., but as the day goes on, 10 a.m., we're a little more productive. 11 a.m., we're a little more productive. 12 p.m., right before lunch, we're at peak productivity. And after that, we eat our lunch in this moment, and it causes us to get a little sluggish until we're finally losing energy by the rest of the day. You know, something like that. And again, different people with different body chemistries and mental capacities have different productivity rates based on when they eat and when they sleep and when they wake and all that stuff. That's just this guy Bob right here. Now, if I pull this back, if I zoom out, you can see that eventually this curve doesn't make sense. First of all, having the curve for less than 0 doesn't make sense because we ain't going to work before 9 a.m. And if we go any later than, what's that, about 1, 2, 3, 4, 5, 6, about 6.5 hours in, all of a sudden, if I trace to 7, we're at negative productivity. So this model is no longer accurate after 6.5 hours. But again, oh geez, that's not gonna work. Let me just do this again. 0, sorry about that, 6, y min, we wanted 0, the y max I think we had at 50. Boom, there we go. So that was a rate. This does not tell us how many we've tested at a specific point, because we're testing more and more and more as the day goes on. So if in the first hour, this productivity is about 15 an hour. So we'll probably do about 15 in the first hour, maybe 16. But in the second hour, our rate's gone up, so we might be able to get 18 done the second hour. Maybe we're going to get 20 done in the third hour, maybe 30 done in the third hour. But then we're going to have maybe only 20 here, and then only 15 here, and then only 10 here. See, this is the rate where our rate is going up and then coming down. So we're still adding people to the pile that have been tested, which is why this is a rate, not the actual number of people tested. If this was the number of people tested, that would say we've tested the most number of people right at noon, and then we've now somehow managed to test less people. So we had, let's say if this was 100 people tested, now an hour later, we only have 90 people tested. That wouldn't make sense. The number of people tested has to go up. It can literally never go down. That's why this is a rate, not the actual number of people being tested. The word rate gives me a clue that we're supposed to be integrating. To find a total accumulation of something, you integrate the rate between the endpoints. So we're integrating from 10 a.m. to 1 p.m. Well, what are those t values? It's not 10 and 1 because t is the number of hours after 9 a.m. Well, 10 a.m. is 1 hour. Sorry, that should be a colon. After 9 a.m. So that makes the t1. And at 1 p.m., that's 3 more hours. So that's a t value of 4. So we are integrating from 1 to 4 the function -3t squared plus 18t plus 15. Now I'm not doing this over dx. These variables are t's, so we're integrating over t. Remember, this dt basically counts as the width, the function counts as the height, and this integration symbol says we are adding infinitely many rectangles from 1 to 4. Where again, the parentheses is the height, the dt is the width. Well, we're just going to do our straight up calculus. Power rules. Add 1 to each exponent, divide by the same value. That's -3, that stays. The t squared becomes t cubed. Since that exponent is now a 3, we divide by the same. Plus 18t, that was a t to the first, so we add 1 and we get t squared. So that's plus 18t squared, but then divide by the same value, which is 2. Plus constant terms, when you integrate, you just throw the variable in there. So 15t, because the derivative of 15t would be 15. If you don't trust me, that was originally, because there is no t, a t to the 0. Add 1 to the exponent, you get a 1, which is here. Divide by 1, and there it is. We do not need a plus c because this is an application, this is an area. We're going between 1 and 4. Now, because of that, some people like to put this in parentheses. Some people say you don't have to. I actually say you don't have to. But again, some people will put this in parentheses in case you might think, oh, we're only evaluating the 15t. That's not correct. I am handling all of the terms between 1 and 4. So we're going to plug in the upper limit, which is 4. Let me actually simplify this first. The -3 and the 3 cancel. The 18 and 2 make a 9. That's -t cubed plus 9t squared plus 15t, evaluated from 1 to 4. So plug in the 4. That's -4 cubed plus 9 times 4 squared plus 15 times 4. Then subtract the lower limit. So minus multiple terms. Let's go ahead and get the parentheses out of the way so we don't fake missing it or actually miss it. Now we plug in the 1. So that's -1 cubed plus 9 times 1 plus 15 times 1. 4 cubed is 64, so that's -64. Now there was no parentheses, so the even or oddness of that exponent doesn't matter. That would be a negative no matter what. Plus 4 squared is 16. 16 times 9 is what? 144. Plus 15 times 4 is 60. The 1 cubed is 1, 9 times 1 is 9, 15 times 1 is 15. This went negative, positive, positive. Distributing the negative makes it go positive, negative, negative. You're distributing the negative, so all signs change. So this negative times the negative makes that a positive. 1 cubed is 1. This negative times that positive gives a negative. 9 times 1 is 9. This negative times this positive makes the negative. 15 times 1 is 15. And then we just keep doing our arithmetic. Negative 64 and 60 make a negative 4. 144 minus 4 is 140. That's 141. And then minus another 24 would be 117. That number gives us our answer. So what that says is between 10 a.m. and 1 p.m., our technician can test 117 people. Integrating a rate gives you an actual value. How did we know this was a rate? We literally had the word rate. But if you don't have the word rate, the clue is per. When you see the word per, P-E-R, not like a kitty cat, P-E-R, not P-U-R, that tells you it's a rate. When you're given rates, you are typically going to integrate if you're asked a question about something involving that rate. So how many people, blah, 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 the rate involved people per hour. So you're integrating over time because it says people per time to get a total people. Total acclimation or accumulation of a rate is the integration of the rate over the appropriate variable. So what a lot of students will accidentally do at first is they'll just plug in the 1 and the 4 into the given function and subtract those. No, you have to integrate the rate. Now again, your calculator could have done all that for you. Because this is a nice whole number, if you actually go to second calc, option 7, and go from 1 is the lower limit to 4 the upper limit, it'll confirm that you get 117 people done basically during your peak productivity times. Now, you're definitely more productive from the next hour, but then you go back to being slower than you were starting at 10 a.m. So if you wanted to know how many people you would get done in that first hour, it would be less than the second hour. It would be less than the third hour. But then from the third hour on, your productivity starts going down. So how many people can you test in the whole day? Let's just see that. So let's do second calc. Let's go option 7. Let's see how many people we can test over this entire day, starting at hour 0, which is 9 a.m., to hour 6, which would be 3 p.m. So now it'll shade the whole thing. And we can see that we can test 198 people out of the entire day. Let me clear my screen by doing this so we can get the graph fresh. Let's see how many people we can test in the first hour. So let's integrate from 0 to 1. 0, 1. So in the first hour, we can test 23 people. How about from the first to second hour? Now this black box is still going to be there unless I go back and just type something so it starts fresh. The calculator doesn't delete the previous areas. So now we had 23 during the first hour. Let's see how many people we get done from hour 1 to 2. So during the second hour. So lower limit 1, upper limit 2. So during our second hour from 10 a.m. to 11 people, we're able to get 35. So we got 23 during the first, and then we pick up 35 in the second. Maybe this doesn't have to do with our productivity as in terms of being lazy or hungry. Maybe this is just the influx of people. Maybe it's not that many people at first, and as we get closer to noon, people on their lunch breaks, you got more traffic coming in. That's another side of the productivity there. So we got 23 from the first hour, 35 from the second hour. How about the third hour? So 23, then 35. How about from hour 2 to hour 3? 41 people. So from hour 2 to 3, we're able to knock out 41 people. Now, this graph looks symmetric based off of the halfway point of noon. It looks like the left side matches the right side. It's not symmetric to any axis. It's symmetric to this peak right here. I'm willing to bet you that if I go from the next hour, I get another 41 people. So let's go from hour 3 to 4. Look at that, 41 people. And then the next one would be, I think it was 35, and then the next one would be 23. So that's how many people we can get for each individual hour. So if you added up hours from 10 to 11, 11 to 12, and 12 to 1, which were 35, 41, and 41, you get 117. So if you add the 35 from hour at 10 a.m. to 11 a.m., 41 from 11 a.m. to 12 a.m., and then the 41 from noon to 1 p.m., you get your 117 people. Guess what? This technician could be testing for a virus going around right now. You can see curves in the media that deal with this. You see the rate of how many people per day are being tested, maybe as a moving average or maybe as an actual finite value. The finite value is kind of crappy because you tend to get a lot more testing on Monday because people aren't testing over the weekend. And that's why they say the moving average graphs are the best. So how do they find out the total number of people that have been tested? They integrate the moving average curve. That's exactly how it's done. It's calculus. And you might say, well, couldn't they just add up everybody? They could, but it's going to take a lot longer to add up all the individual tests than to just integrate over a curve. Now, do they have actual polynomial functions for those moving averages? No, they don't know the exact function that makes the shape because it's a weird, wacky, super crazy shape. So you know what they do? They go back to numerical methods. They have infinitely many of those little rectangles, and I don't mean infinitely, they have like 100,000 of those little rectangles, and they let a computer program find all those 100,000 or million areas, add them up, and then they get the total number of people infected. So this is really good stuff. And I usually don't do an infection problem for this class, but it seemed relative this semester, so I did. I usually do more economic stuff, but like I said, I really like this. I actually took an economic problem and put a, a twist on it.
Just changing videos real quick. Really, 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 really long title. Properties of definite integrals. The additive property, average value, moving average. So we're going to do more of this integration stuff, obviously. What do I want to say? We might not get to moving average. I don't think that we're going to be able to cover that, but we'll definitely do this additive property and average value. And you might think, well, you've already covered the additive property. You said that if you have the integral of x plus 2, just think about them independently. It's a different additive property. It's actually usually feels more like a subtraction property the way that we're going to use it, but let's just hold off on what that really means for now. So what we're building to ultimately is the area between two curves. That's what that first topic is really getting on about. So if you're given functions f of x and g of x and asked to find the area between the two curves on boundary
A comma B. In other words, from A to B. So from the first number to the second number, those are x values. So those are x values. So if given functions f of x and g of x, so two curves, and instead of you wanting to find the area under the curve, because now I got two of them, maybe you want to find the area between the two curves. And we'll get a picture for that very, very shortly. But if you're asked to find the area between the two curves, from a first x value to a second x value, a and b, this is equivalent to the following. The integral from a to b of f of x minus g of x dx, but only as long as f of x is bigger than g of x on the entire region. Sorry, give me a second. How do I want to do this? Sorry about that. I had a question. So to find the area between two curves, you're just doing integral area. And if you're given your functions f of x and g of x, and you're asked to find the area between the two curves on a boundary, so again, a left and a right boundary, you're just doing a subtraction of the two functions and then integrating from a to b, as long as the first function is greater than or higher than, as a picture, the second function on the entire region. Now, that entire region is what gets a lot of people. So there's a couple issues here. First of all, you've got to know which function is higher. How can you figure that out? Well, plug some x values in. Plug an x value in. Plug the a in and see if f is higher than g. Plug the b in and see if f is higher than g. Now, just because one is higher at the endpoints doesn't mean that it's higher across the whole region, though. So we'll get into all the math behind that. But here's the picture I said we'd get to. And we're just going to keep this mostly in the non-slanted first quadrant. So let's do f of x in red. So here's our f of x. And let's do g of x in blue. And they can look like any curves in the world. And then let's have x values being a and b here. So maybe it's like from 1 to 10 or from 2 to 5, something like that. So the area that we are finding is this. That would be the area we're finding. This integral represents this two-dimensional space. You have to go f minus g because the red f is higher than the blue g. And it's true across the entire boundary from a to b. Now, this doesn't always happen. These functions can crisscross. And if they crisscross, you'll have to account for that. But we'll hold on to that idea for later. So what's happening? Why does this actually work? Well, let's think back to the idea of when we said, all right, the integral gives you the area from 0 up to a point. So when we wanted to go with just one curve, the area from a to b instead, you took the area up to A and you subtracted it from the area up to B because you needed to cut that little chunk off. We were thinking about cutting horizontal chunks off previously. Now we're trying to cut this chunk off down here because when we do the area for F, it's going to give us the whole thing. Let me draw all this up for you. So if I just do, let me try and keep these the same as best as I can. Something like this. Here's our f of x. This area right here from a to b represents the integral of f of x dx from a to b. This area right here again from a to b that represents the integral from a to b of g of x dx. That doesn't look like a b, that looks like an a. This blue area right here, I'm going to draw it on the left one really quickly and then I'm going to erase it. What this blue area is exactly is this area right here. So the red one is the entire thing under the f of x down to the x-axis. The red one represents this. And the two to the side, the red one represents the whole thing. But the blue one represents this chunk below, which we don't actually want, which is why we subtract it off. That's why this works geometrically. There we go. The red one is the entire area under the F curve. The blue one is the entire area under the G curve, but we don't want the area under the G, just the area above it, but below the F. So you're basically finding the entire area down to the x-axis. Then you're finding the entire area below the curve down to the x-axis and taking it away. That again is what this statement says. Now again, if these crisscross anywhere, you'll have to break it up into multiple intervals. So I want to write that down. And I've said it several times, but let's write it down. However, if at any point, meet, swap, whatever you want to call it, cross, you'll need to break up this integral into several intervals. Let's pause on that idea and come back to it after we do an example. Okay. No new formulas, really. I mean, you can argue this is a formula, but I mean, it's just a subtraction. I don't call subtractions formulas. I call it concepts. So example 1. Do I need an A? Do I need an A? I do not. Find the area between the two curves, A to B. And this will be f of x equals 3x squared plus 4. Then we'll have g of x is going to be 2x minus 1. And we're going to go from x equals -1 to x equals +2. So I'm going to take a shortcut on showing that one of these functions is higher than the other, because it doesn't have to be the f minus the g. Again, this is determined on which one is higher. You always have to subtract the higher than the lower. Higher minus the lower. Right now, I don't necessarily know which one of these is higher. So what you might do is, one thing you can do is graph it if you are allowed a calculator. Let's pull out a calculator. Let's see what these bad boys look like. Where were we? I don't need that little calculator right now. Okay. So we got 3x squared plus 4. The leading term there is x squared. This is going to look like a parabola. Then we got 2x minus 1. That's a line. You should already know what those look like, how they should bend, how they should change. Now it's going to graph them one at a time. So when I hit graph, that's the first one. That's the f of x. And there's the g of x. So again, that 3x squared plus 4, that is this one right here, the parabola, that U shape. The g of x is a line, 2x minus 1. And here is that line. So when you look at this, and we're only looking from -1 to 2, this window is from -10 to 10, and this entire window, at least what we can see up to here, this curve is definitely above the line. Again, the curve is the f of x, the line is the g of x. So based on the graph, based on the graphs, f of x is bigger than g of x on, it's supposed to be in red, oh well, on -1 to 2. Again, all I did was graph it. If you're not allowed a graphing calculator, well, hold on until the end of this problem and I'll show you what to do. Again, that curve is definitely higher than the line in that region. So we need to do the integral from -1 to +2, f of x minus g of x. We got to do the first one minus the second one. Don't forget your dx. Don't forget your parentheses when these are more complicated like that. But let's actually write what the functions are. The f of x is the 3x squared plus 4. So this is the integral from -1 to 2 of 3x squared plus 4 minus the g of x is 2x minus 1. So we do like this, right? Question mark, question mark, question mark. No, that's wrong. Need a parentheses. Because the g of x has multiple terms and it's being subtracted, you gotta wrap it in a parentheses. This kind of feels like when we're doing the endpoints. But we're not even to that point yet. We're still evaluating the integral. And then don't forget your dx. So because it's a double parentheses now, I'm gonna use a bracket for that outer one. This was the f of x minus the g of x, and then over the dx. Now, what some students might do is they'll do the 3x squared plus 4, they'll plug in the 2 and the -1, and they'll get the upper area, the whole thing. Then they'll do this integral of 2x minus 1 by itself. They'll plug in the 2 and the 1 into that, and then they'll get the lower one, and then they'll subtract those two numbers. And that's fine, but this is a shorter way to do it. It's going to be less work. Just combine your like terms and then do the integral. So this is the integral from -1 to 2 of 3x squared plus 4 minus 2x plus 1, because we're distributing the negative. Watch your arithmetic rules. Then that's over dx. Combine like terms. You get the integral from -1 to 2 of 3x squared minus 2x plus 5. Because the +4 and the +1 made a 5, dx. And then we've got a pretty simple integral to do. It's all power rules, and arguably a power rule with a 5, arguably the constant rule. It works either way. So add 1 to each exponent, divide by the same value. So for the first one, that's an x squared, becomes an x cubed. Leave the 3 in front. Now it's an x cubed, and you divide by that same number. It's not because there was a 3 in front that I'm dividing by 3. It's because this new exponent's a 3. Minus, leave the 2 alone. This exponent is originally a 1. Add to that and you get 2. So x squared, divide by the same number as the new exponent. Plus, that's a linear term, so, I'm sorry, that's a constant term, so its integral is a linear term, 5x. We do not need a plus c because we're doing the actual area. So that's where we just do that little vertical bar and say we're evaluating this between -1 and +2. Again, there's a couple different notations for that. I'll see some people just wrap it in a bracket. I think that's what our textbook does. Our textbook will take this and bracket like so. I'll show it the textbook way once, but it's actually the only textbook we've had in a long time that did it this way. I'm used to seeing the vertical line. So again, doing it this way is the same as writing it this way. There's no difference. I will show the textbook's way for once, though. Before we do the evaluations, let's reduce the 3's and the 2's. So this is x cubed minus x squared plus 5x, and then we're evaluating that between -1 and +2. Those are the upper and lower bounds. So let's plug in the 2 first. We get 2 to the third minus 2 to the second plus 5 times 2. That's plugging in the upper limit. Then a minus sign. I like showing that minus sign in a different color for emphasis. Minus. Now we're plugging in the lower limit, but the lower limit, there's multiple terms to plug in, so we got to wrap it in parentheses. Probably going to need about the same space. And we're plugging in a negative, so we'll need more parentheses there. So that's -1 cubed minus -1 squared, both with parentheses, plus 5 times -1 with a parentheses. Let me tell you, it sucks really, really bad. It's really frustrating for students when they know their calculus formulas and then they lose lots of points because of the arithmetic. Calculus is the sum of arithmetic, geometry, algebra, and some people will say pre-calculus, but I mean, that's literally called pre-calculus because it's the stuff you need for calculus. It's just advanced algebra. It also involves trigonometry, but we skip that in our class. All of those things have to be mastered. Okay, so what do we got? 2 cubed is 8, minus 2 squared is 4. The minus is not part of the squaring, so leave it alone. Plus 5 times 2 is 10. Minus parentheses. -1 cubed that way is -1. Minus, now that minus I just wrote is this minus symbol right here. -1 squared in parentheses is a +1. It's not +1 though, because again, there was a minus outside of that. Then the plus 5 times -1 makes a -5. Distribute, you get 8 minus 4 plus 10, plus 1 plus 1 plus 5. 8 minus 4 is 6, plus 10 is 16, 17, 18, 23. I feel like I did something wrong. 8 minus 4 is 4. I think I said 6. 8 minus 4 is 4. 4 plus 10 is 14, 15, 16, 21. I had to check my arithmetic there for a second. I was rushing. Almost made a mistake. So the area between those two curves is 21. Now maybe you don't trust this. I like a TI-83 to back up our non-trusting feelings. So I can only have one of these on at a time in order to use this for any calculator. I believe there are some Texas Instruments where you can swap it between them. Maybe this one, maybe not. I'm not going to spoil that. But let's just leave one at a time for now and hold on to the number. So let's put the 3x squared plus 4 up, graph it, and let's find the area under that from -1 to 2. Why did I hit that? Let me hit this. So let's go to option 7. Lower limit, -1, enter. Upper limit, +2, enter. And we get, why did I do that? I forgot it does that. -1, +2. We get 21, interestingly enough. All right, so hold on to that number. That was 21. You might say, oh, well, that's the same answer, so we're good. That is a little weird. So hold on to that. The area under the curve, under the first curve was 21 to the x-axis. Now let's I'm just going to turn that one off. If I hit left and then enter, that turns it off. Now let me put the 2x minus 1 up. See, that curve's no longer there. Here's our line. And let's do the area, -1, +2. And what's interesting is that area is 0. That is why if you have the area under the first curve being 21 and you're subtracting off the area into the second curve, which is 0, it's still 21. This does not usually happen. This is kind of a weird, I don't want to say special case, it's just an oddity. Odd man out. And that's because the area on this left lower triangle, which is below the x-axis, counts as negative. This one counts as positive. Those two things basically just cancel each other out. So again, when you actually draw this up, I turn both of these on. What we've really found is the area between these two curves. So this no longer just goes down to the x-axis, it actually goes below it, which is why there's a little bit of a negative area there. Let me draw that up here. Don't do that word, you're being silly. So what our picture looks like. Our line is down here, and this is just a quick sketch. That was our g of x. Our curve was up here. That doesn't look symmetric, and it is. Let me try again. There we go. So there's our curve, and we are going from -1 to +2. So the area that we're finding it actually extends all the way down here. That's the area we're finding. This little spot right here, I'm going to shade it in real quick. This little spot is not part of the area. We're not shading that in. It's the area between the two curves. The x-axis is no longer necessarily a boundary. When you're doing an area under a curve, you always assume that the x-axis is the lower or upper bound. When you're doing the area between two curves, we no longer care about the x-axis, which is why this area is going below it and this one is above it. So we use this cutout, but not this cutout. All right, so now that we've seen pictures and we've affirmed our thoughts, and I forgot to write f of x up here, that's okay. What if you weren't allowed a calculator?
And we'll talk about that when we come back. We're going to go ahead and do our break. So let's say we're going to pick back up at 7:57. All right, so stretch your legs, do whatever you got to do. We will pick up back at 7:57. And we're back. So let's pick up where we left off. What if we didn't have it?
Or what if you don't know how to use your graphing calculator? What if you don't have a graphing calculator? You need to algebraically show where one function is higher than the other. Do this by evaluating f and g, f of x and g of x, at both endpoints, as well as setting them equal to each other after you do all that first part to see if they ever cross. So going back to that example with the f of x being 3x squared plus 4 and the g of x being 2x minus 1. We said f of x was 3x squared plus 4. G of x was the 2x minus 1. And we were going from -1 to 2. So we'd have to do f of -1, which would be 3 times -1 in parentheses squared plus 4, which is 3 plus 4, and that's 7. Then we'd have to do g of -1, which is 2 times -1 minus 1, which is -2 minus 1, and that's -3. At -1, f is greater than g. F of x is bigger than g of x. 7 is bigger than -3. So that says that if you drew them out, the f function, the parabola, should be higher than the line, and we saw that already. Now let's do this at the right one, f of 2. So f of 2 would be 3 times 2 squared, that's a times, not a minus, plus 4. 2 squared is 4, 3 times 4 is 12, that's 12 plus 4, which is 16. Whereas g of 2 is 2 times 2 minus 1, which is 4 minus 1, which is 3. So at x equals 2, 16 is bigger than 3, so f is bigger than g again. So at the left endpoint, the f function is higher. At the right endpoint, the f function is higher. And what you might think is, as long as it's higher on the ends, then it's always higher. But what if our f function does this, and our g function does this, and we're going between here and here? I didn't set that up right. Wrong endpoints. I want to be here and here. I forgot to label G. So on this graph, on the left point at A, right here, the red's higher than the blue. F is greater than G here. At the right endpoint at B, the red's higher than the blue, so F is greater than G. But look at this. Look at how many times they cross. They cross here, they cross here, and they cross here, and they cross here. They cross 4 different times. Because after A, after you cross here, the blue is higher than the red. And then after this one, the red's higher than the blue. And then after this one, the blue is higher than the red. And after this one, the red's higher than the blue. Every time they cross, you would have to make a whole new integral under a whole different region, whatever those 2 regions are. But the point is, just because you're higher for one function on the left and higher for one function on the right doesn't mean that they're always higher in between, which is why we have to do that other jazz. You have to, as well as setting them equal to each other to see if they ever cross. If they ever cross, they typically change which one's higher and which one's lower for a while. And then you can go and say, all right, well, here's an X value in that range, which one's higher, which one's lower, if you need to affirm that. So are there any crossing points, also known as intersections? So you set f equal to g, which is 3x squared plus 4 is equal to 2x minus 1. That's a quadratic equation, so you need to move everything to one side and set it equal to 0. So you're going to subtract 2x on both sides. You're going to add 1 to both sides, which would give us 3x squared minus 2x plus 5 is equal to 0. I'm going to shortcut you some work here. This is not factorable. The AC method, 3 times 5 is 15. I'm sorry, hold on. 1 and 15, 3 and 5, 5 and 3, that's positive. Yeah, this is not factorable. It looks like it might be, but it's not. That's prime, which means you'd have to go through and do the quadratic formula, ... And you would end up with imaginary solutions. And that's because your b squared is smaller than your 4ac. So quadratic formula, remember that's negative b plus or minus the square root of b squared minus 4ac all over 2a. I've been telling all my students in pre-calc, you never ever get to forget that. Where your a is 3, your b is negative 2, your c is 5. So you go x equals negative b, so that's negative negative 2 plus or minus square root. B squared is negative 2 in parentheses squared minus 4 times 3 times 5. That's your 4ac all over 2a, which is 2 times 3. That's positive 2 plus or minus. I'm doing this quick because I just want to get to the point. Square root of 4 plus 4 times 5 is 20. 20 times 3 is 60. All over 6. You know what, I said that was prime and it's not. How is that going to work? Hold on, I might be rushing too much on my own. B squared did all that right, didn't I? 4 times 3. That's not a plus. Why did I say plus? There's my problem. I thought that was a negative that I wrote there, and I would have written that in properly. 4 times 3 is 12. 12 times 5 is 60. There's one single negative in there, so that's supposed to be minus 60. I was getting really confused for a second when I saw a positive number inside the square root all over 6. This is 2 plus or minus the square root of negative 56. This is what I was expecting, all over 6. Because we don't know the square root of negative 56, that's why this is prime. This is the square root of a negative, which means you pull out an I. So this is 2 plus or minus I square root of 56 all over 6. I don't even care about simplifying this anymore. The I means there's no real solutions. This was discussed very heavily in pre-calc. It means these two things never cross. The picture seemed to back that up as well. If you go into the graph of them, they don't look like they're going to cross because this on the left side is going to keep going up forever. It's definitely not going to cross the line that's going down forever. And it's a parabola which grows quicker than the line, so this thing's going to go up a lot quicker than this line is going to. If you don't believe me, let's zoom out. There's our parabola. There's our line. They're never going to cross. So the fact that f was higher on the left and right and they never cross tells us that we only have to do this as one single integral over one single interval. All right, so let's take this idea and let's do a word problem. So that was example 1. Example 2. A company marketing high-def TVs expects to sell them at a rate, there's that word rate, that rate usually means we end up having to do an integration of 2e to the 0.05t. That's a 0.05t, and this is in thousands of sets per month. T is the number of months since available. However, with additional advertising, using a sports celebrity, well-known sports celebrity. Okay. They should sell at a rate of, see if I can squish this in here, 3e to the 0.1t. This is a higher rate. The coefficient has changed from a 2 to a 3, that's bigger. And then the exponential coefficient went from a 0.05 to 0.1, that's double, that's bigger. Advertising helps you sell stuff. Fact. Using celebrities helps you sell stuff. Fact. So what this is saying is the rate of TVs sold per month in thousands of sets is this lower value if you don't advertise, and it's a higher value if you do advertise. And that, of course, is in thousands per month. So the ultimate question is, how many additional sales result from the endorsement? During the first year. I have to be careful with that. I said first year, whereas our T is in months. Now, I will admit this one would be a pain in the butt to do the algebra that we just did. These are not polynomials and quadratic. You can't quadratic formula your way out of this. Graphing is the best way to tell which one is higher and which one's lower. And the good thing is they're not going to swap. So how do we know that I'm going to end up doing an area between two curves? Because we have two different rates that we're comparing, and we want to know how many additional sales would result. So let's pull up our graph. And let's have the function 3, then e to the 0.0, oh, this is supposed to be the 2e to the 0.05, x, can't do t's, and the other one was 3, e raised to the 0.1x instead of a t. Let's fix the zoom to standard. So this is the one with the 2 coefficient, and there's the one with the 3 coefficient. Now, this variable is in months. T is in months. T is in months. And we're trying to do this over the first year. How many months are there in a year? There's 12 months. So this window, I should technically extend it to 12 for the x maximum to get the full picture. And I can even, if I don't want to see the negatives because we're not looking at negative months, I can make the x minimum 0. And this is the entire picture that we should be looking at. You could even cut the y part down here if you wanted. See if the whole thing ends up there. That's good enough. You can see that the second one, the one with the 3, is higher than the other one, the first one. So if I call the one with the 2 F and the one with the 3 G, F is bigger than G on 0 to 12. Why do I care about 0 to 12? Because that's the first 12 months of a year, and we're looking only at the first year. Not on 0 to 1, on 0 to 12. And I just wrote something wrong. G was higher than the F. The F was the lower one, the G was the higher one. And if you're not sure, you can trace. When you're tracing along a function, it shows you which one you're on in the upper left. So this lower one is the 2. If I hit up, it transfers me to the other one, 3 e to the 0.1x, and that's higher. So we said G is higher than F. So that's the order we have to do the subtraction. So what we are trying to ultimately do is find the area between these two curves from 0 to 12. We're trying to find all of this area, not below, just between the two curves. That would be the additional sales. The reason is, when we integrate the rate, we get the sales figures. So if you just integrate the 2 e to the 0.5, that would give you the sales from no advertising. If you just integrate the 3 e to the 0.1, that would give you all the sales from advertising, because integrating the rates gives you the sales. So if we integrate this difference of them, that would subtract off all of the sales without advertising from all of the sales with advertising. So we got to do the integral from 0 to 12. Let me switch to red now, which I should have already done. I keep forgetting that. Not the end of the world. 0 to 12, and we're going to do g of t, our independent variable is t now. G of t minus f of t. And we're integrating over dt. So this is the integral of from 0 to 12 of the 3e to the 0.1t minus 2e to the 0.05t. I'm doing brackets instead of parentheses. That's just a personal preference. Now we're going to need to integrate each of these using formulas that have previously been provided. As a reminder, the integral of e to the ax dx is 1 over a times e to the ax plus the c. If needed, it won't be needed here. Do we really need the 1? No, we can just put it over the a. That's the format of these. Now the 3 and the 2 are going to stay out front, so we have our 3. Then we have our e to the 0.1t, but because there's that 0.1 as a coefficient in the exponent, we divide by the same thing. We're not adding 1 in this instance. This is not a polynomial, this was an exponential. Then the minus 2, leave the exponential term alone, so e to the 0.05t, but divide by the coefficient in the exponent, so 0.05. And then we're evaluating this between 0 and 12. Let's clean this up first. 3 divided by 0.1 is 30. Dividing by a 10th is the same as multiplying by 10. Dividing by a 20th is the same as multiplying by 20. So that's going to be a minus, oh, hold on with the e term, e to the 0.1t minus 40 e to the 0.05t, evaluated between 0 and 12. Now let's do the evaluations. Let's plug in the 12 first. So 30 e to the 0.1 times 12 minus 40 e to the 0.05 times 12. That was us plugging in the upper limit, so minus. Now let's plug in the lower limit. There's multiple terms, so we'll definitely need a parentheses. So we're plugging in 0 now, so that's 30 e to the 0.1 times 0 minus 40 e to the 0.05 times 0. Please also remember that anything raised to the 0 is equal to 1. You've got to know your rules. So this will be 30 e to the 1.2. 0.1 times 12 is 1.2 minus 40 e to the 0.05 times 12 is 0.6. Distribute the negative appropriately. So this is a minus 30 times e to the 0 is 1. This negative and this negative, the blue and the red cancel, so that's a plus. Leave the 40. And this e to the 0 is going to be another times 1. E to the 0.1 times 0. 0.1 times 0 is 0. E to the 0 is 1. 0.05 times 0 is 0. E to the 0.05, I'm sorry, e to the 0 is 1. These first two e terms you're stuck with because they're not 0. And we certainly don't know what either of those are. But the last ones we do. So what we get is 30 e to the 1.2 minus 40 e to the 0.6. That's a minus 30 plus 40, which is a plus 10. That is the area. This was an application though, right? I probably want to see decimal values when we're talking applications, because if you bring this to your boss is not going to care. He wants to know, what number is this? What in the world? E, I don't know what E is. Give me a number or you're fired. So the approximation you would need a calculator for. So we get 30 times e to the 1.2, close the parentheses, minus 40 e raised to the 0.6, and plus 10. And we get about 36.7. Now remember, these were measured in thousands of sets per month, so integrating over months just gives us thousands of sets. So this would be 36.7 thousand sets, but not over 1 month because we did this from 0 to 12, so that was 12 months in 1 year. Is this how many we sold? No, this is how many additional sets we sold because we advertised. Maybe we sold 10,000 sets without advertising, and that means we would have sold 46.7 thousand sets with advertising, and that difference would be the 36.7. So this is an increase due to advertising. If you wanted to know them independently, second, calc 7, and I can use the up and down to switch between them. So let's do the 2 first. So this is the no advertising curve. It's a lot less steep. It's not growing as quickly. It's lower because advertising helps. So let's go from 0 to 12, 0, 12. And that area is 32.9. I'm just going to write that for a second, 32.9 to hold on to that. Now let's do it again, but on the upper curve. So let's go second trace, option 7. Let's hit up to go to the upper one, lower limit of 0, upper limit of 12. Now remember, I didn't clear it, so it's not just doing that area, it is doing the whole area. And it's 69.6. And guess what 69.6 minus 32.9 is? You guessed it, it's 36.7. So we had 32.9 thousands of sales of TVs over a year without any advertising. But when we throw the advertising in, we get 69.6 thousand sets, which means there was an addition of 36.7 thousand sets in a year. Now, I can't get these answers with algebra. That was calculus. You still had to integrate to get them independently. But instead of doing them separately, you can just do it this way, which, believe it or not, is actually quicker. Especially because it's not always entirely accurate to do the areas one by one. If they crisscross, you can't do this second bit. If they ever crisscross, you cannot do that second bit, which is why I'm not actually officially showing you anything. I'm erasing it, but just showing you for that problem where they don't crisscross that you could have. All right, I'm going to give you a minute just to soak that in case you're still writing. And then we'll move on to the other scenario. What do we do when they cross? We've already talked about that. We already basically showed a scenario, but it had ugly answers because they didn't cross. The next one will be much nicer. So that was example 2. Next up, we're on example 3. I don't know where that was. Find the area between the curves. And I'm not going to write them as f and g this time. I'm going to go back to the y equals, because who says you can't do that? So between y equals 12 minus 3x squared and y equals 4x plus 5. I'm a big fan of one of them being quadratic and one of them being linear, but that does not have to be the case always. It just gives them less opportunity to crisscross. And then this is from x equals 0 to 3. There's your two curves. And I am not going to graph them this time up front. This time, we're going to take an entirely algebraic approach at first. So we need to find out what it looks like on the left side, what it looks like on the right side, and if they cross at all. So let's do at the zeros. If you want to go back and label these as f and g, you can. But I'm going to try and label them unlabeled just because not everything is labeled as a function. So at x equals 0, I'll just call them the first and the second instead. The first, you get y equals 12 minus 3 times 0 squared, which is 12 minus 0, which is 12. The second one, that's y equals 4x plus 5, so 4 times 0 plus 5, which is 0 plus 5, and that's 5. So on the left, the first is greater than the second. What about on the right, at x equals 3? The first one, we get y equals 12 minus 3 times 3 squared, which is 12 minus 27, which is negative 25. And 3 squared is 9, 9 times 3 is 27, 12 minus 27 is negative 25. The second one, that's y equals 4 times 3 plus 5, which is 12 plus 5, and that's 17. So they do cross at some point, obviously. So at the right, not soon, so on the right, the second is greater than the first, which means they clearly cross. Remember, just because they are the same doesn't mean you can't say it's a lot of negatives that they don't cross. Just because one function is higher on the ends does not mean they cross. If they cross twice, That means at one point the second one's higher, and then at one point the first is higher, and then it goes back to the second being higher, or vice versa. But this definitely says they cross. Again, once again, I'm repeating this a lot because it's important. If they cross an even number of times, it is possible that the one function is higher on both ends. So even if you get the same declaration, the first is bigger than the second, first is bigger than the second, you still have to do this next step. We set them equal to find the intersections. So that's 12 minus 3x squared is equal to 4x plus 5. Now there's an x squared term, so I want everything to go to the one side. I don't like the leading term being negative, so I'm going to move everything to the right. I'm going to add 3x squared to both sides. I'm going to squeeze it in front of the plus 4x, and I'm going to subtract 12 on both sides. So everything on the left is now gone, and we get 0 equals. The 3x squared is now positive on the right side. The 4x is still positive. The 5 minus 12 gives us a negative 7. This is factorable. Whether you use the AC method or trial and error, that is up to you. Trial and error is not too bad because there's not a lot of options here, so we get 0 equals. But if you're big on the AC method, again, just make sure you know how to do that. The 3 times the 7 is negative 21. Then you're trying to find a pair of numbers that multiplies negative 21 and subtracts to 4. And then you split the middle term up. You'll have 4 terms, and then you factor by grouping. Again, that's on you to remember that. I'm just going to take this quickly and go with the AC method. Since the first term is 3x squared, this has to be a 3x, and this has to be an x. There's literally no other options. Since the last term is a 7, it's got to be 1 and 7 or 7 and 1. And you can trial and error it to figure out which way it works. It turns out the 7 needs to go here and the 1 needs to go here. That way the outer product is 3, the inner product is 7, and 7 minus 3 is 4. We need to make sure that that difference comes up to a positive 4, which means the larger product needs to be positive. The 7 gives us the larger product. 3 times the 1 gives us the smaller product. So that's your factored form. Then we zero product rule this. We set 0 equal to 3x plus 7, and we set 0 equal to x minus 1. Do your algebra, subtract 7 on both sides. You'll get 3x equals negative 7, or negative 7 equals 3x. For the other one, you'll add 1 to both sides, which tells you 1 equals x. That one's solved. This one, you still got to divide both sides by 3. To get negative 7/3 is equal to x. These are the 2 points where they cross. But do we really care about both of those points? Maybe we do, maybe we don't, depends on the problem. We are only observing the region from 0 to 3. We're going from 0 to 3. Negative 7/3 is not in that window. So ignore it. All we care about is the x equals 1. This is the point at which they cross, and we will see this graphically when we finish all the algebra. The first example we did graphing, then algebra, so I wanted to flip-flop it here. So we're integrating from 0 to 3, but not quite. So since they cross, can't just integrate 0 to 3 in a 0 to 3 in a single integrand. We must make 2 integrals, where the first goes up to the crossing point, and the second starts at the crossing point. So the area between the two curves, 0 to 3, is, we do an integral from 0 to 1. We have to go from 0 until the crossing point, and then the order of the two functions has to be appropriate. Is it the first one minus the second, or is it the second minus the first? Well, starting at x equals 0, the first was higher than the second. So we got to go the first minus the second. This is kind of poorly written, again, because I intentionally did not write them as f and g's. If you did, it would be f of x minus g of x. So this would be the area up to the first crossing point. Then you add the area from the crossing point until where you're ending. Now, if there are multiple crossing points, you'd have to do this again. Let's say they crossed at 2. I'd go from 1 to 2, then another integral from 2 to 3. Now, when they crossed, they switched. See, when they switched up from 1 until 3, now the second one is higher than the first one, so we got to swap that order. We're going to do the second minus the first over dx or dt or whatever the variable would be. Let me go ahead and show you the picture so that you can kind of follow along with this, so you can really see that they do cross and one ends up going higher than the other. So what were our two functions? We had 12 minus 3x squared, that was the first. And then the second was the 4x plus 5. So that's another quadratic and a line. So the first one will be a quadratic, the second one will be a line. Let's go back to standard zoom. So there's our parabola and there's our line. Look at that, they cross at that negative 7/3. There's the first cross that we ignored because we only cared from 0 to 3. And then they cross up here. In fact, because we only care about 0 to 3, let me make that window from 0 to 3. And I don't have quite all of the parabola in this. I don't have quite all the line in this. So let's pull out on this. Let's make the y maximum maybe 20 would do the job. And I still don't quite have enough below on this curve, so let's make the y minimum negative 20. And that should do the trick. All right, so the area we're finding is this region right here, and then this region right here. Where do I want to put this? Trying to decide how much room I'm going to need for this. I think I can do it down here. So here's our parabola, basically. Here's our line, and they cross at 1. So let's have this be the 1. So here's 1, and then here's 3. The area that we're finding is this little chunk right here, and then this chunk going up to the 3. That's the area that we're currently finding. And see, over here on the left side, the first one is higher than the second one. It's to this point where the second one is higher than the first. This was the second, this was the first. So again, you can see here, the first one is higher than the second one. So if you want to find the area appropriately, you have to go the upper one minus the lower one, but then they swap, which is why you can no longer go first minus second, because the second is higher, you have to go second minus first. That is the reason why these are swapping. That is the reason why we break the integral up to any points where they cross. So now let's actually go and do our math. So equals the integral from 0 to 1. the first minus the second. That was 12 minus 3x squared. Then minus, and you'll need a parentheses for the second function. And the second function was 4x plus 5. So this is the red one. I'll keep the colors. Then the blue ones, that's first minus second. The second's got multiple terms, so parentheses. Then plus, integral from 1 to 3. Second minus first, you're just swapping the order of these things. So it's 4x plus 5 minus parentheses 12 minus 3x squared. Then all over dx. Now, there's some cool features here. There's some annoying features here. It feels annoying because you're going to end up doing a lot of the same arithmetic and algebra. So that's slightly annoying because it feels like you're doing twice the work for one. But I would say actually, at least these aren't completely different things. Let's see what I mean. So the first one, integral 0 to 1. I'm going to do all this in one fell swoop to save myself some space. Distributing the negative makes that a minus 4x and a minus 5. Let's go ahead and put these in a more appropriate order. Let's do the negative 3x squared first, then the minus 4x. We have a positive 12 and a negative 5, so that's a plus 7. And then that's over dx. And then the next one, integral, is from 1 to 3. This negative is going to be a positive 3x squared. Then we have the positive 4x term. Then 5 minus 12 is negative 7. Note that the red and the blue are complete opposites from each other. That will happen 100% of the time. When you swap the order of subtractions, the answers are opposites. I forgot my little plus sign here. Let me just squeeze that in. It's not a multiplication of integrals. Good Lord, what would that be? Plus. So again, notice the red and the blue are now just opposites of each other. So you can actually use that, if you remember that consistently, you could use that fact to save yourself some algebra and some arithmetic. All right, let's do the evaluations now. Let's do the integrations. Add 1 to each exponent, divide by the same. Leave the coefficients. That's negative 3, x to the third over 3. Added 1 to the 2. 3, divide by the same value, minus 4, x squared over 2, plus integration of a constant to linear, 7x. And we're evaluating that from 0 to 1. And plus. Now, these are going to be the same, just opposite in signs. So that's 3x cubed over 3 plus 4x squared over 2 minus 7x, evaluated from 1 to 3. Please let me move this graph. Thank you. So equals. Let's clean these up some. That is negative x cubed minus 2x squared plus 7x, evaluated from 0 to 1, plus x cubed plus 2x squared minus 7x, evaluated from 1 to 3. And it's instances like this that might really be helpful, instead of using my notation of these lines, to do them as brackets instead, like the textbook does. That might be more helpful for you visually. All right, let's plug in the ones, the upper limit. So that's negative 1 cubed minus 2 times 1 squared plus 7 times 1. Then minus parentheses, plug in the lower limit, 0. It's going to end up with a bunch of zeros. Negative 0 cubed minus 2 times 0 squared plus 7 times 0. Now let's do the upper and lower limits on the other one, with just opposite signs of everything pretty much. So that's plus 3 cubed plus 2 times 3 squared minus 7 times 3. That's plugging in the upper limit. Minus parentheses to plug in the lower limit. Plugging in a 1 gives us 1 cubed plus 2 times 1 squared minus 7 times 1. A lot of arithmetic there. A lot of opportunities to make mistakes. All right, negative 1 cubed, that's a negative 1. 1 squared is 1 times negative 2 is negative 2. That's a positive 7. This whole parentheses is 0, so that's a minus 0. Plus 3 cubed is 27. 3 squared is 9. 9 times 2 is 18. Minus 7 times 3 is 21. Let me go ahead and distribute the negative. 1 cubed is 1, so that's going to be a minus 1. 1 squared is 1 times 2 is 2, so that becomes a minus 2. 7 times 1 is 7, but that's a double negative, so it's a plus 7. Fun fact, these, when you end up plugging in the same limit one time as an upper bound, one time as a lower bound, they're always going to be exactly the same. Look at this, -1 minus 2 plus 7, -1 minus 2 plus 7. They're always going to double up. Some people think they should cancel on plugging in the same number twice, so they cancel, but no. Because when you plug it in the first time, these count as positives. When you plug it in the second time, you end up subtracting it, and you're plugging it into the opposite of the original function, and 2 wrongs make a right. All right, finally, let's do all of this combination. -1 minus 2, that's -3, plus 7 is 4, plus 27 is 31, plus 18, that's 23, minus 21 is 2. Wait, I did something wrong somewhere. I think I subtracted there, didn't I? Let me start over. -1 minus 2 is -3, plus 7 is 4, plus 27 is 31, plus 18 is 49, minus 21, that's 48, 28, minus 1 is 27, minus 2 is 25, plus 7 is 32. That should be right. 3, 4, 31, 49, 28, 27, 25, 32. Good. That is the area between the two curves. This would be a pain to check because you would have to do 4 separate areas in your calculator. You would have to do the first one from 0 to 1, the second one from 0 to 1, and subtract them in that order. Then you'd have to do the second one from 1 to 3, the first one from 1 to 3, and subtract them in that order. There's a lot of opportunities for you to flip things around and make simple mistakes, and then everything falls apart. If you get a negative answer, I can tell you this, you're wrong. The area between two curves should never, ever be negative because this is more of a geometrical sense. Two curves. Because we're not considering ourselves in relation to an x-axis and considering everything below an x-axis negative anymore. We are no longer under that mindset. Now, yes, if you do the individual integrals, you are under that mindset. But when you start subtracting two functions, you are no longer considering yourselves related to the x-axis or relative to the x-axis. So there should never, ever be negative areas. They are always positive. So if you get a negative area between two curves, that is a sign that it's wrong. I'm not saying you can't ever have a negative area. When you're looking at one function, you can have negative areas. It's when you're finding the area between two curves. All right. What kind of time we got? Do we have the time? Now I got a Green Day song stuck in my head. So again, there was the picture for it. That was the area. Again, yes, if you were just doing the area of the first one, it would have considered this chunk right here to be a negative area if you were just thinking about the area of one function. When you're doing it between two curves, it is now counting as that chunk as being positive. If you end up with a negative area, you either messed up your arithmetic somewhere probably, or you forgot, or you had a intersecting point and you didn't account for it. Or maybe you just had the functions completely backwards and you weren't actually thinking which one's higher than the other one. Quadratic functions aren't always higher than linear ones. We just showed that. The first example, the quad was higher than the linear. The linear can always be higher than the quadratic, or they can crisscross. Don't assume too much. I actually wish this was a little lower. Let's put it under the picture. There we go. There we go. All right, so that was example, oh, wrong button. This boy right here. That was example 3. Let's go to example 4. And I'm going to start this out with an example without setting it up. I'm not going to tell you, ahead of time, hey, this is what you do. We're going to have to figure it out. Find the area bounded by the curves. Now, I usually write this as a y and a y. I'm going to switch it to f, though. F and g. So let's go. F of x is equal to 3x squared minus 12. And g of x equals 12 minus 3x squared. That is the whole problem. I did not forget to write anything. What is different about this versus the last few? I'll give you a second to catch up and write. Find the area bounded between the curves. F of x equals 3x squared minus 12, and g of x equals 12 minus 3x squared. What's different about this? And no, it's not the fact that these are just opposites of each other. That is true, they're opposites of each other, but that's not what I'm pointing out. What I'm pointing out is, in this last example, find the area between the two curves from x equals 0 to x equals 3. Look at the one before that. Find the area between the two curves from x equals 0 to x equals 12, because we were looking at 1 year, or 12 months. When we did this one, find the area between the two curves from -1 to 2. Let's go back to what we're on now. Find the area between two curves. Well, wait a minute, Mr. Beckner forgot to give us the bounds. There's no bounds given. Well, how are we supposed to know how to integrate? How do we know what the A and B are supposed to be? Let's look at the graph and let's see if maybe we can deduce this. So let's go back to this. Oop, too much. 3x squared minus 12 and 12 minus 3x squared. Zoom 6. So there's the f of x, there's the first one, and there's the g of x. So I'm going to retrace these. I'm going to pause it. So I paused it. That right there is just the f function, 3x squared minus 12. You should all know that that's an upward facing parabola because the biggest term is an x squared and it's a positive coefficient. Now I'm going to hit enter and unpause it, and it's going to draw the second one, 12 minus 3x squared. That should be a downward facing parabola. So here comes our downward facing parabola. Here's the g of x. So that's the picture we're looking at. And you got some cutoff. Let me just zoom out just a little bit. Let's make the, the window. Let's make those y values the minimum, maximum. I think -20 and +20 are good enough. Just because it looked like they were pretty close. There we go. So our graphs, why does it keep doing that? Here's our graphs. Our f of x looks something like this. That's not very symmetric looking. In fact, that horizontal line looks terrible. A little better. Here's our f function. It looks something like this. That looks more accurate. That's the f. And the g function looks something like this. Not too bad. Ooh, that arrow is terrible, though. No! Oh, well, the right one's fine. So there's our g function. The area that we're trying to find is the area bounded by the curves. Do you think you have an idea of the area we're trying to find? I didn't give you an A and B. I didn't tell you to go from, say, 0 to 12. If you go from 0 to 12, it looks like you'd have this open space that you'd have to cut it off, or 0 to 9, or anything like that bigger. What I'm suggesting is that you're probably finding this area right here. And not probably, you are finding that area. That is the area bound between the two curves. So in other words, you can find the lower and upper bounds based on the intersecting points. This right here, whatever that value should be your A, is what your A should be, and whatever value right here should be your B. Let me just put it as a written note to the side. The A and B should be the intersecting points of the graph. Now, if there's more than two intersecting points, that's a problem you won't have in here. It would just be two intersecting points. How can you find them? Well, I got my T83, so I can just trace it and find out where it is. Is it 1? Doesn't look like it. Is it 2? Yeah, it kind of looks like 2. How about the other one? Is that -2? It looks pretty symmetric. Y value 0. Yeah, it's -2 to 2. But let's assume that you don't have your calculator. Let's do it algebraically. How do we find intersecting points? We set them equal to each other. So set, once again, F equal to G to find these. So that's what we're about to do. So we set F of X equal to G of X, which is 3x squared minus 12 equal to 12 minus 3x squared. Well, this is quadratic. The biggest term I see is an x squared, so let's move everything to one side. Let's keep those terms positive, the biggest term that is, so let's add the 3x squared to both sides to make this easy, and thus subtract the 12 on both sides, which should give us 6x squared minus 24 is equal to 0, which is easy to factor. There's a GCF of 6. You'll pop that out. You'll be left with x squared minus 4. That's a difference of squares. So that's 6 times x plus 2 times x minus 2 equals 0. Set all three of those things equal to 0. 6 equals 0. X plus 2 equal to 0. And x minus 2 equal to 0. The first one is trash, so we throw it away. Subtract 2, add 2. I'm not showing that work this time. You get -2 and +2 as your intersecting points. This is where they cross. I, P, intersecting points. And that confirms what we saw graphically, that they cross at -2 and +2. That tells us our integral. Now, we have already seen the graph. We have seen that the g of x is higher than the f of x. But let's just prove that anyways. Now, you can't do the a and the b this time because they're going to match. F of a is 0. G of a is 0. F of b is 0. G of b is 0. At the intersecting points, they match. So just evaluate at any x value between to show f is bigger than g or g is bigger than f on that interval. Well, 0 is between -2 and 2. That's the easiest one to do. So let's do f of 0. Which would be 3 times 0 squared minus 12, which is -12. And let's do g of 0, which is 12 minus 3 times 0 squared, which is +12. Therefore, g is bigger than f, as our graph confirms. If it's bigger on that point, it's bigger on all the points before they cross again. All right, so that says the integral we need to do is g minus f, and we're going from -2 to 2. So we are finally to the point where we can say our integral is going to go from -2 to 2, and we've got to do the g of x function minus the f of x function. On that interval, the g is always higher than the f. So this would be the integral of -2 to 2. The g of x was the 12. And let me go back to doing this in two colors. The g of x was the 12 minus 3x squared. Then minus the f of x was the 3x squared minus the 12. But because we got to make sure we're subtracting that, we wrap it in parentheses. And this is all evaluated over dx. Ooh, that was terrible. Let me just erase that. I didn't use the different colors to represent different integrals. I just used the different colors to represent the f and the g here. That's all I did. I don't have to break this into multiple integrals. The last example, they crossed at some point, which is why we had to do the integral from the left point to where they cross, and then where they cross to the right interval, and swap the order of the f and the g's in each of these. That didn't happen here. See, the last example crossed. They switched from being higher and lower. This one, they never actually cross in the boundary we're integrating over. Where they crossed is what we use as the boundaries. It's kind of a different scenario. Now, maybe I told you to integrate from -5 to +5. That would be a completely different problem. There would actually be 3 integrals, because we'd have to go from -5 to -2, then from -2 to +2, then from 2 to +5, and keep swapping the order of the f and the g each time. This is simpler. All right, let's distribute the negative, so we get the integral of -2 to +2, 12 minus 3x squared minus 3x squared plus 12 over dx, which would be the integral from -2 to +2. The 12 stack, the -3x squared stack, so that's -6x squared plus 24. It's actually not a coincidence that this is the same thing that we saw when we were solving the equation. It could be opposite in sign potentially, fair warning. But the terms in magnitude are the same. So this would be, now we can integrate it. Adding 1 to the exponent divided by the same value, that's -6, leave it alone, x to the 3rd over 3. Plus the integral of 24 is 24x. And we're evaluating from -2 to +2. The 6 and the 3 reduced to a 2, so that's -2x cubed plus 24x, going from -2 to +2. Let's plug in the +2 first, so that's -2 times 2 cubed plus 24 times 2, minus lower limit, so parentheses, -2 times parentheses -2 cubed plus 24, I need a little more room, plus 24 times -2. There we go. -2 cubed, I'm sorry, 2 cubed is 8 times -2 is -16. That was this term. 24 times 2, that's a plus 48. Minus, I'm going to leave the parentheses alone for now because that's a lot of signs. -2 cubed is -8 times this -2 is positive 16. The 24 times the -2 is a -48 inside the parentheses. So this will be negative 16 plus 48 minus 16 plus 48. Negative 16 plus 48 is 32. This is really just 32 plus 32, which is 64. You don't have to add them in that order, but it was convenient because of the symmetry. Sorry. I had the word similarity stuck in my head. I needed to say symmetry. So the area between those two curves, based on where they cross, is 64. Again, you don't have to do an integral that way. I could have told you to integrate from 2 to 9, or negative 5 to positive 5, or 0 to 12. But because I didn't describe bounds, the implication is that you'll use where they cross as the lower and upper bounds. So there's a variety of types of problems with these integrations. Sometimes they cross, sometimes they don't. Sometimes you're given the upper and lower bounds, sometimes you're not, and you have to find them analytically, algebraically, graphically, whatever. All right, so that's a pretty good set of examples that cover all the different types we could see pretty much. We've had exponentials. I mean, you could have a natural log in there somewhere, a 1 over x that leads to a natural log. It's the only thing I didn't quite cover for these examples, but we've seen those integrations. It's nothing new. The last topic of the section that we'll get to is the average value theorem. And this states that the average value of a function f of x on a bounded interval a to b equal to the following. So your average value, again, from a to b, is equal to 1 over b minus a integral from a to b, and then it's just the function integrated. Some people just write this a little differently. Some people choose to write it this way: integral a to b f of x dx over b minus a. This is one and the same because this b minus a is a constant. We've said you can pull constants out of integrals. They don't really affect them. How does this relate to an average? An average says add up everything and divide by the number of things. That average definition is true for what we call finite elements. This is based on an average of finite elements being add the elements and divide by the number of elements. This formula is for continuous elements. The 1 over b minus a is basically dividing by the number of elements. But we don't have to start at 0. It's not to say, oh, we have 10 marbles, so divide by 10. We could be including marbles -1 to +9, which 9 minus -1 is +10. And the integration of the function is basically adding up the elements. What is really happening is we're finding the area and dividing by the width to get the average height. That's what's really happening. We are taking we know this area sorry, I'm trying to get all this on the screen at once. There we go, perfect. We know the area is equal to the integral from a to b of f of x dx. This area right here. Now, let's make a new picture. And let's have this right here, this line, be the average height of f of x. And we're still going from a to b. We know this area is equal to the length times the width because it's a rectangle. The length, or let me go with the width. Actually, I wrote length first. The length is the height. We're calling length height in this case, width is width. So the L, that's the average height of f of x, which average height means the average. So that's the average times the width. The width is b minus a. Now in these two pictures, if you take this function and you twist it to just a flat line that is literally the average of the function from a to b, and I should say from a to b here. So if I took this thing and just flattened it out, but I made these areas the same, these areas are the same. This area on the left is the same as this area on the right. So by flattening out the height to the average height between A and B, these areas would be the same. If you added up the infinitely many rectangles of this left one, that number would match adding up the infinitely many rectangles of this right image. So if the areas are the same, that says this integral should be equal to this thing right here. So this thing right here, which is the area of the left thing, should be this right here, which is the area of the right thing. So we're going to set those equal to each other. We get the integral from a to b of f of x dx is equal to whatever the average is from a to b times b minus a. Pull up this formula right here. It's solved for the average value. How do you solve for this average value? Divide both sides by the parentheses b minus a. To get the formula. That's where this average value theorem comes from. It says that the average from any 2 points a to b is the integral from that a to b divided by the width from a to b. So I gave us a nice little typed up summary of what's going on, kind of in a really basic idea, then the calculus idea. We've got images. We claim that the areas have to be the same, so we set the area of this thing equal to the area of this thing. That is exactly how someone derived this average area formula. This is one of the few proofs we do. So you have to memorize this. How do you find an average value on a window of a function? You divide by its width, and then you just integrate it. That's all this says. Divide by the width and integrate it. Integrate it, divide by the width. So we'll do one of these in our last...
As I was saying, as I was about to say, we will do one of those next time when we come back. So we have almost finished 4.4. So that'll be due a week after that. So what's that, the 11th? Just to give you a little extra time. So 4.3 is going to be due on the 4th. and then we will just keep pushing forward. Not too many days left of this class. It's kind of crazy. This was what, our 10th meeting. So we have 4 or 5 more, and that's it. Semester flies by, right? All right. So as always, if you have any questions, you can shoot me an email. But besides that, have a good evening, study hard, work hard, and we'll see you next Monday. Take care, everybody.